let's use a piece of line of a quarter lambda length for another purpose. In this case, what we are going to assume is we are going to provide a total reflection termination. In this case, just a short circuit. So we solder here the two wires at the end of the line. So we short circuit at this point. This means the voltage at this point has to be zero. The current, of course, would not be zero, but the voltage at this point is zero. So we have this termination impedance equal to zero. It's a particular case of the previous situation. Then, what's going to happen? Well, if we calculate the impedance here at the input of the line, we have this expression. And for the particular case when the length is a quarter lambda, actually this tends to infinite. And that's quite surprising. This means that if we apply here some power, there's no current at this point. This is what this expression means. And this is a total reflection situation as well. So a wave that progresses here to the right is going to have a total reflection coefficient, -1 in this case, and when it goes backward, the reflection goes backward and reaches the input port, we have again a total reflection situation, in this case with a gamma equal to 1. So actually we have here a piece of a standing wave situation, where we have waves going back and forth, and they can be sustained in time. I mean, if we have a lossless situation, we will have here a permanent situation with a voltage distribution which will drop from this input towards zero at the output of the line, and the intensity is going to describe a similar sinusoidal behavior, but the other way around. So we have a maximum of intensity at the output, but zero intensity of the input. And this situation, if we have a completely lossless situation, stays forever. So if we actually launch a wave here, we'll be sustained here forever. Of course, in reality, if we have losses, this will be some decay with time, and this situation will be progressively going towards zero. But what is interesting is for the particular case, and that's important, when we have a signal and a length of the line in such a way, giving the frequency of the signal, the length is exactly a quarter lambda. This can sustain a standing wave that stays forever in a lossless situation, or for a very long time if we have a very low loss situation. And that's interesting because this is a resonant condition, because this is only true for a very precise frequency when this is exactly lambda divided by 4. If the length is not satisfying this condition, this actually will drop very quickly. We can actually make a mechanical model for this. So if you consider at the end of the line you have a zero voltage, and at the open side of the line voltage has an important amplitude parameter. This is the same as this tuning fork. When you actually, this motion can be more or less analogous to the voltage along the line. And you know, a tuning fork is very resonant. I mean, it only works for a very defined frequency, and that's why it's used for tuning musical instruments, for example. And so this actually is a bandpass filter at the end. So it only sustains a very particular frequency or its harmonics. And we can use this to make filters. So a very important device in communication applications is to be able to design filters that only propagate signals at a very precise frequency or band of frequencies. And you have an example here on the right. So this filter, this is an input port and an output port. These ports actually communicate to transmission lines. And there are many transmission lines here which are coupled together because they are sharing the same cavity here. So each of these transmission line is a quarter lambda resonator. And here the frequency of tuning of every one of these resonators can be adjusted with this screw here. But the important thing is these are particular cases of transmission lines. We have a short circuit here on one side and an open circuit at the other, and this is a resonant structure, okay, as we have seen before. There are other possible situations when we can actually make a transmission line resonant. For example, if instead of using a short circuit at one side and an open circuit at the other, we have just to provide 2 open or 2 short circuits at both ends. So in this case, you have here a description for the open circuit case. We have a description of the intensity and the voltage along this transmission line. And when the transmission line is exactly half lambda, it is also resonant, because when you start from one side, reflect to the other, and you come back, you get exactly the same situation. And this happens only for a very precise frequency, or its harmonics, higher harmonics. You see here, this is actually has an analogy, for example, again with musical instruments. For example, you play guitar, and you take a look how the string of the guitar is vibrating. It's actually vibrating in the fundamental mode like this. And this is exactly the same situation as the intensity here, if you see, in the electrical case of the transmission line. And if you play guitar, you know you can make your strings to resonate at higher harmonics. And this describes how is the vibration, or how is the mechanical excitation of the string happening in the higher harmonics case, and this is also happening here. So this is also, you can also make this resonant for higher frequencies, for example, multiples of the initial or the fundamental frequency here. So the condition is, again, intensity have to be 0 at the ends, and then the voltage is maximum, and then you have a resonant condition. You have here an example of a filter. When you see each one of these lines is half lambda in length.